Hi, welcome to another round of interesting observations from the world of music. Where I wanted to actually go is I wanted to show the projection of all the 12 notes on the flute. But before we go there, we actually need to understand the relationship between these 12 notes, their relative position on the scale, so that when we project them onto the flute, it all makes sense. So in order to do that, I would like to share with you this set of frequencies I have here. So I have the notes from C to B, the 12 notes, and I have 1 to 8, which is a total of 9 octaves, and our middle octave is here. So this is our middle C. So the frequency of our middle C is 261.63 hertz, and our standard A is 440 hertz. So what we should do is next, let's take these 12 notes and just copy them here, and let's carry these 12 frequencies from here and let's paste them here as well. Okay, now because this is cyclic, we need to get the 13th note, which is the C on the next octave, right? So I'll add a C here, and the C on the next octave, the frequency is here, which is 523.25 hertz. And so I'll copy that and I'll bring it over here. Okay, so that's our 13 frequencies, C to C. So this is our C on the lower octave. And then the same C, same note in the higher octave, immediately next higher octave is. Okay, so those are the two notes, the same C on two adjacent octaves. So there is a level of similarity between them, meaning those two notes are actually C and they sound similar in the sense they are sounding C. However, one is shrill, the higher octave one is shrill compared to the bass octave. So they are dissimilar in that sense. So what exactly is this relationship between two notes that are an octave apart, right? Let's see that. Let's take this one, the higher C, and divide it over the frequency of the lower C. Aha, what we see is 1.999961778, which is almost 2. What this is telling us is that the frequency from the lower note to the higher note is exactly twice. It's double, 1 to 2. That's why they sound similar, and after that it's actually a repetition of the cycle, right? And this characteristic is pretty much inherent to the waves. That's how the waves behave. It's not something that we create, but that's how the waves are. Now it's not just C to C. If you take any note to any note, you take D to D or D sharp to D sharp, any of these notes one octave apart, they're always double the frequency. So now we understand that is, when you are defining a range of frequencies for an octave, here is your bass and here's your top, and this is double. So in between you have to fit 12 notes, right? So how to do that? One thought, intuitive thought would have been to take the difference between 523.25 and 261.63 and divide it over 12, make it into 12 equal parts and add it to all of them. But that's not what was done, right? Now let's observe what was actually done. In order to figure out what was actually done, let's add a formula here in this cell. So what we shall do is we shall take the immediate adjacent notes frequency and subtract from it the current note frequency. Okay, so it's for C, when we take the difference between C and C sharp, it is 15.55 hertz. That's the difference. If you do that for all the notes, what you see is that It's 15.55, 16.48, 17.47, 18.5, 19.6. So it's increasing. So it's not a constant equal addition that they have done, but it is increasing. But we just talked about, 12 notes and then equally dividing the 12 notes. So this does not seem equal. What's going on here is they have done it equally, but not in an additive way. The reason is like this. Take this analogy. Let's say you're carrying some weight, okay, and you're carrying this weight, and let's say this is 100 pounds, okay. Then I add 10 pounds to this. That's 110 pounds. Then I add 10 more pounds. Then it's 10 pounds on 110 pounds. It does not feel the equal. It does not feel equal as 10 pounds over 100 pounds, okay? Because when we say equal, it is with respect to what you're carrying. Initially, I'm carrying 100 pounds. So 10 pounds is 10% increment. But then I'm carrying 110 pounds. So in order for me to feel the difference to be the same, this time I have to take 10% of 110, which is 11 pounds, I believe. So I need to add 11 pounds to this to make that equal increment. And that's how I need to keep incrementing. And the same is true with pitch as well. That is, when your ear is listening to one frequency and then you want to increment it equally, you need to increment it in terms of percentage or a fraction and not in terms of addition. Okay, so that's exactly what is done here. So let's observe how that is true here. So let's do this. We've taken these differences between adjacent notes, right? Let's look at what it is as a fraction of the note that we are on. For example, let's take C and C sharp. The difference between C and C sharp is 15.55 hertz. Now, this 15.55 hertz divided over the base note C's frequency is 0.59. Now, let's see what values we have here. So we've got everything to be 0.0594394. Everything is 0.059. And after 0.59, you see a little variation. They're not all the same. But it's a variation in the fourth decimal place, right? But otherwise, if I express all of these as a percentage, all of them are 5.95%, or about 6%, right? That is how they have divided all the 12 notes in between these two bounds. That's a magical 6% or 5.95% if you want to be accurate. And that's how the notes are equally placed, so that as you're moving from one note to its adjacent note, you always get the same increment, and your hearing, your brain can listen to the same increment. That's how they are equally spaced, even though additively they are not equally spaced. Hope I'm clear about what I'm trying to describe here. Now, one thing that I want to show here is that if you look at this fourth decimal place, after that there are variations. They are not all exactly the same, which means even in terms of percentages, they're not precisely placed equally. So depending on what they are putting their emphasis on, there are different tuning systems. So the one that we are looking at is equal temperament tuning system, where they try to place every note equally distant from the previous note, right? But there are other tuning systems like just intonation, and even there are more tuning systems in which they laid the emphasis on a different aspect. For example, in just intonation, they place the emphasis on the third and the fifth intervals being accurate. And you can definitely go and read more about those types of tuning systems. But essentially, coming back to this, what we are seeing is that it's actually the magical 6% increment that is applied to every note. There is another interesting thing that I want to show here. Let's take these notes. Let's make a copy of these notes. And what we shall do now is let's get rid of all the sharps, right? And repeat that for all. Okay, So what we see is that 12.25% and 5.95%, right? And now you look at these frequencies, we got how many 12.25%? 1, 2, 3, 4, and 5. So 5 notes that are 12.25% apart. And then how many 5.95s? 1 and 2. 2 notes. 2 notes that are 6% apart and 5 notes that are 12% apart. 5 and 2, right? Does that show a pattern? It does. That is, whether you take Indian music or Western music, you always have 2 notes that do not have sharps, right? So in Indian music, they happen to be sa and pa, and in Western music, they happen to be B and E. None of them have a sharp, right? So you see why, because when you have divided these notes into 12 notes and then you arrange them like this, then everyone goes by 6% increments, and then when you arrange the sharps, there are 2 of them that cannot have sharps, and that's exactly what you see in the frequency pattern as well. They could have been given a different set of names and a different convention could have been followed, but it's not followed. So for whatever reason, they followed this convention and they chose 2 of them not to have sharps, and that's what this is. Now, we might also ask the question, why only 12 notes? Why not make them 24 notes, right? Why don't you divide them equally by the same multiplicative method and then create 24 notes? We could have, and actually there are certain systems that divided notes into 24 instead of 12. So that's called microtonal music, and there are instruments that are made to play microtonal music. So each frequency gap is further subdivided into 2 pieces, and so you could actually play the note in between them, and you can look up more on microtonal music and listen to it, and that's probably the limit of human ear. That is, beyond that, if you further subdivide, it wouldn't make any sense, because we cannot actually distinguish the difference between those frequencies. There is a point at which we stop distinguishing the difference in those frequencies, and microtonal music itself is already at a point where it's hard for me to distinguish the difference between the notes, but some people can. So that's about that. So it is about the 6% magic and about this 5 notes being at 12% of 12% distance, and then only 2 notes being at 6% distance, which is what the fundamental for our note system is, right? So that's what derives our 12 notes, and how those transpose or they get projected onto a flute is something that we will discuss in another conversation. But in this, I wanted to bring out this relationship between notes so that you can appreciate why 12 notes and what the difference is and what these sharps are and how all these notes are mathematically related in that octave bound by the beginning frequency and the ending frequency. Hope you enjoyed that, and see you next time around. Thank you very much.